Hi guys, welcome back to Physics 145, and this video can also be used for Physics 150. Okay, for the chapter number 10 that we have here is magnetism, right? Chapter 10, magnetism, everything to do with magnetic field. All right. So the first thing is we want to look at what is actually magnetism. So let's assume you have a piece of magnet. All right, we have a piece of magnet here, north side and a south. So try to draw in a three-dimensional manner here. So I have this north, and here is the south, right? So this is the north pole of the magnet, and this is our south pole of the magnet, and we're going to have this magnetic field. Okay, so the magnetic field is defined to be pointing from the north to the south. Okay, like that. That is our magnetic field, and the magnetic field normally is given a symbol B. Okay, and it is a vector quantity, so I have to be very careful with magnetic field. It's a vector quantity. Now let's say you have a you have a piece of conductor, a piece of conductor that actually pass through, the magnetic field, like this. And furthermore, that conductor is carrying a current of, let's say, I. It carry a current I. So what happens is, if you have a conductor that carry current I, and you put that conductor inside a magnetic field, that conductor is going to experience a magnetic force. Okay, it's going to experience a magnetic force. So our magnetic force here, let's assume again one more thing, is that your conductor, the total length of conductor that is inside the magnetic field is this length. Let's say we call this one L. Okay, the rest are not inside the magnetic field. Here, only the dotted part is inside the magnetic field. So that means the magnetic force is only applied to this part, to this part length. All right, and since I put this one like that, so physically it is 90 degrees. So the magnetic field cut through the conductor that carry the current at 90 degrees, or we say perpendicular. So the B and the I is perpendicular, or the B and the displacement L is perpendicular. All right, this is displacement L here. So this is our displacement L. They are vector. Okay, now the force experienced, the force experienced by the magnetic field, right, is actually depending on three factors. Three factors. Number one is the size of the current. Number two is the length of the conductor exposed to the magnetic field. And number three is also related to the magnetic field itself. That is the strength of the magnetic field. The strength of the magnetic field. And then furthermore is it also depends on the orientation of your conductor. If your conductor is like parallel, the current flow is parallel with your magnetic field, you got zero force. But when your current flow is perpendicular, or when your length or the displacement is perpendicular to the magnetic field, the force experienced by the conductor is maximum. Maximum. So minimum, maximum. So we have magnetic field parallel. Let's say this is the magnetic field that we have here. So blue color magnetic field, and this is a conductor. If they are parallel to each other, then you experience zero force. Anti-parallel also zero force. But when you are like this, perpendicular, you get maximum force, or like that. That is maximum force. But if you are at a certain angle with the magnetic field, like this or like that, then that force, will be in between zero and maximum. So that one related to the angle between them, which is more accurately depending on the sine of the angle between them. We call the angle here theta. So that is the situation that we have. So we know that our force, is directly proportional to the magnetic field strength. The force also directly proportional to the current magnitude, and the force also directly proportional to the magnitude of the length. and at the same time the force is also directly proportional to the sine theta. The angle is the angle between the direction of the displacement L and the magnetic field. We'll look at that one in more detail in the subsequent part later on. So we can actually combine all of them, we get this. Okay, so this one is equal to ILB sine theta. Alright, so now let's assume in our case, okay, if the theta is 90 degree, right, theta 90 degree here, so our F is equal to ILB only. Alright, so our magnetic field is equal to the force, which is the maximum, divided by the I and the L. That is where we define our magnetic field. Okay, the meaning of magnetic field. So I'm going to define this magnetic field. Okay, definition for magnetic field here. So magnetic field B is defined to be the maximum force, okay, maximum force experienced by 1 meter, okay, by 1 meter of conductor, okay, that carry 1 ampere of current. Okay, or we can say magnetic field B is the maximum force experienced per unit length per unit current. Okay, so our B is this one. So B is equal to the force divided by the I and the L. So our magnetic field units will be Newton per ampere per meter. Okay, per ampere per meter, and this one has a special name. This one is called Tesla. Okay, unit T, and the older unit for Tesla is actually called Weber per meter square. Okay, or this one have a units of WB per meter square. This Tesla and Weber per meter square are equivalent. Okay, equivalent. But of course, we have other units for our magnetic field. Okay, other like CGS unit. Okay, for B magnetic field is Gauss. Okay, is Gauss, G, which stands for Gauss. Okay, Gauss. So 1 Gauss is equal to 10 to the power negative 4 Tesla. Alright, so to give you the feel of how big is 1 Gauss, so let's look at the Earth's magnetic field. Okay, our Earth's magnetic field, B Earth. On the surface, now what you are feeling, the compass, where the compass is actually moving because of the magnetic field, that field is about half a G, okay, about half Gauss, which is 0.5 10 to the power negative 4 Tesla, or 5.0 10 to the power negative 5 Tesla. This is our magnetic field for the Earth, okay, for the Earth's surface. Of course, it's near Earth's surface, yeah, near Earth's surface, because the further you go away from the Earth's surface, it becomes weaker. Now, that is example of the other unit CGS. Alright, so Gauss, but Gauss is not in your syllabus, so you're going to stay with Tesla and also Weber per meter square. Alright, so most of the time we use Tesla, but 1 Tesla is a very strong magnetic field. In our lab, normal lab, is quite difficult to produce a strong magnetic field like up to 1 Tesla, so that's why we use normally milli Tesla or even micro Tesla. Okay, so that is a meaning of magnetic field. Now we want to look at the force on a conductor, or sorry, the force on a charge. Okay, the force on a charge. So first, this part here, A, is magnetic field B. Okay, magnetic field B. Now the next one is the force on charge particle. Okay, on a charge particle, okay, in a magnetic field. Alright, so that charge must be moving. Okay, the charge must be moving, or a moving charge inside a magnetic field. Yeah, moving charge. Okay, so forgot to put in, it's a moving charge. If the charge is not moving, it cannot experience that field. So let's assume our magnetic field here, okay, point to our right hand side. Okay, point to our right hand side. Okay, and that is B. We are talking about a constant magnetic field, B, to your right hand side. And then there is a charged particle enter. Okay, a charged particle enter. Let's say this charged particle enter at a velocity V. Okay, at a velocity V, and that means it is making an angle theta here. See or not? Okay, it makes an angle theta, and the charge we assume is a positive charge, and it have a value of Q. Alright? So a charge moving with velocity V, and then has a inside a magnetic field B, and it have a charge of Q. Now the force experienced by this by this charged particle is given by this. Okay, the force I will give you in a vector formula. So F is equal to Q, the magnitude of the charge, multiplied by the cross product between the velocity and the magnetic field. Now, what is cross product? You already learned, right? Cross product is actually equal to V, magnitude of V, multiplied by magnitude of B, multiplied by sine theta. Okay, multiplied by sine theta. So normally this one we sometimes just throw away. So this one is just to show you this is the magnitude. Okay, why we only show magnitude? Because there is another thing which is a direction. Okay, the direction. Okay, so we simplify it. F is equal to Q VB sine theta. But you need to remember both. Okay, because you must be good at vector. Okay, you must be good at vector. So we have now equation number 1. This is equation number 2, and this is equation number 3. Alright, so that is the formula used to calculate. Okay, but now the next one is we need to know the direction of the force, because force is a vector. So now there are two ways to use. One is Fleming left hand rule, another one is Maxwell screw rule, right hand rule. It's just right hand grip rule. Alright, so first we try to use Fleming left hand rules. Okay, Fleming left hand rule. So direction of force can be determined using number 1, Fleming left hand rule. Okay, and then number 2 is right hand grip rule. Okay, you grip something, grip rules. Alright, first we try to use Fleming left hand rule. So this one is actually quite difficult to draw. So I will just show you in this video. So our thumb, see, so this one is a 3-dimensional thing. So now our thumb, okay, is the force. The pointing finger, okay, in the index finger, this one is the direction of the magnetic field, and the middle finger here is the current. So now I know that current is related to the charged particle. If the charge is positive, the direction of the movement of the charge, a positive charge, is the direction of the current. And be careful when it comes to electron, because electron, when the direction of the electron is, let's say, to the right. If, for example, if this one is electron, if it moves in this direction, that means the current is in the opposite. Right? In the opposite, that one you have to take notice. Yeah? Now, we want to know in what direction is this charge is going to experience the force. So first, we point to the magnetic field. One more way to easily remember is this one. Yeah? This one is FBI. Okay? F stands for force, B magnetic field, I is the current. So you always watch movie, something to do with FBI and whatever, right? So CIA and so on. So FBI is easier. Now, we point to the direction of the magnetic field first. Okay, this one, magnetic field. And then after that, follow the direction of the current. Now, this charge is moving in that direction, right? So it's a positive charge, so our current in that direction. So now we have to turn around. So now, because the angle is not 90 degrees, so the angle between the B and the I should be less than that. But anyway, your thumb is pointing into the paper. So that means the force experienced by this one, I will draw it here, is like this. This symbol says that the force is into the whiteboard. So that means if we have a three-dimensional situation here, you have a charged particle moving in that direction. So what happens is the charge is going to experience the force into the paper. So what happens is the charge, by the time it enters, is going to swing inwards. Okay, and if the field is big enough, it's going to make a circular motion. Okay, so when you see a charged particle moving inside a field and it is making a circular motion, you can confirm that that field must be a magnetic field at least. Okay, so that is one way using Fleming left-hand rule. Now another one is using right-hand rule. Right-hand rule actually is much easier. You can do it mentally also. Now first you look at the formula V cross B, right? Velocity cross B. So first you point to the direction of the velocity here, assuming positive charge, and then you do like this. There are so many ways you can point to the direction of V, 360 degrees. But there's only one way you can bend your finger after that, because you cross B, you have to bend your finger to the direction of B. I believe this is the only way to do so. If you want to do that, you ask your friend to break your finger to do that. Okay, so this one also cannot. The other side also cannot. There's only one way. There are 360, but only one way you can bend your finger to B naturally. Then naturally, so when you can do that, your position of your palm is already correct. Just straighten up your thumb point into the whiteboard. The paper. Alright, so both can give you the method, but this one you have to be careful, because sometimes angle can be more than 90. So imagine you are doing tests, okay, in the exam hall, you have this type of angle, and finally you cramp your fingers or come out your hand like a handicapped person, right? It's not nice. So warm up your hand before you do any question involving this one. Okay, all right, so that is the first one, force on a charged particle that is moving inside a magnetic field. And one more precaution here, we don't allow the charge to accelerate here, only constant velocity V. Okay, next one is the force experienced by a conductor. We already know the equation because we use that one to define magnetic field B. So there's a C, force on current carrying conductor, a conductor that carry current. Okay, so we still need magnetic field. So we draw the magnetic field here, this direction here, and one more here. Okay, then this one. So this again is a constant magnetic field. Okay, this is our constant magnetic field B, and then we put a conductor inside. Okay, we put a conductor inside. Let's say this conductor is like that. Okay, so we want the whole conductor to be inside there. Okay, to be inside here. So now I call this end here P, and this end here is Q. So we know that the displacement of our conductor here, okay, the displacement of the conductor, calculating from where the current start to flow in. So this is our displacement. This is L. Okay, we don't use distance here, displacement. And then the current, okay, the current is flowing from P to Q, starting from here. So this is our current I. Okay, our current I. So now our displacement is actually making an angle theta. Okay, making an angle theta. So we normally can choose, you can draw the angle with the displacement or the current, because they are the same as long as the rod don't bend. Okay, as long as the rod don't bend. So we have that, right? Now we have all the required information, magnetic field B, length, displacement L, and also current I. Now the force, okay, the force in a vector form is given by this. Force is equal to I multiplied by the displacement cross magnetic field B. See, that is our first the equation to calculate the force on a current carrying conductor. So this one is our equation number 4. Okay, that is going to be our equation number 4 now. All right, now we calculate the magnitude. Same thing like before. The magnitude of the force is ILB sine theta. Okay, ILB sine theta. So you need to know both here. So this one is equation number 5. Now, sine theta, the theta is the angle between them. Now, how to get the F maximum? If you want to get your F maximum, you have to make sure that your theta is 90 degree, right? 90 degrees. So when your rod or the conductor is perpendicular to the magnetic field B, that is your largest force. Okay, the force experienced by the conductor is the maximum. When you put this one parallel, okay, it becomes 0. Theta 0 sine 0 is 0, so the force is 0. And then if you turn the rod to the other direction, become anti-parallel. So when it is anti-parallel, the angle is 180. Sine 180 also 0. Right? So if you are parallel or anti-parallel, force 0. Same thing like a charged particle. If your charged particle moving parallel in the same direction as the magnetic field, or anti-parallel or opposite direction to the magnetic field, because the theta is 0, either 0 or 180, so you got 0, the force is 0. So remember the effects, yeah? Anything parallel or anti-parallel is a magnetic field, when charged particle move, you get 0 force, okay? 0 force. Alright, so that is our force on current carrying conductor. Alright, so only 2 formula is actually quite easy for this part. The difficult one is coming now, which is the D, which we're going to call it Ampere's law. Okay, Ampere's law. Well, I'm going to go very slow on Ampere's law. The actual one is like this. You have a, it's actually from a guy, a scientist called Andre. Okay, Andre Marie Ampere. Okay, Andre Marie Ampere is a scientist after Ørsted discovered something. And then Ampere go for further to do some research on the magnetic field and the force and so on. So I discovered something, okay, the relationship. This Ampere law has something to do with current in the conductor and the surrounding magnetic field. We are going to use this one to derive another 2 more and 3 more formula. Alright. So Ampere's law states that it's not that easy to understand. There will be a lot of drawing involved in Ampere's law. Now, we assume we have a conductor, okay? We have a conductor that carry current upwards, okay? Carry current in this direction, let's say, okay? In this direction, so our current is orange color, I, okay? I, and then we know that surrounding that conductor is going to be magnetic field. So it's a circular magnetic field, so we just simply draw something with this. Here I'm going to use blue color, okay, blue color. So my blue color is here. This is the one in the front, okay, and then the one you cannot see is behind, like that. Okay, the magnetic field is like this, okay, and then we know that from experiment it was discovered that the magnetic field are actually following right hand rule again. The thumb go to the direction of the current, so point up. So now imagine that this is a conductor. Okay, this conductor carry current up. So when you hold the conductor like this, you point your thumb upwards. So what happens is, if you see from the top, it actually moves anti-clockwise from our point of view. So the magnetic field will be in this direction. Okay, in this direction, yeah. Okay, now of course we want to know how strong is a magnetic field around this area. Okay, we want to know how strong is a magnetic field at this area. Okay, so we need to look at the whole thing from above. Okay, from above, so it's easier for us to solve the problem. All right, now I'm going to draw this here. Okay, so this is our second page. Now I assume the conductor, okay, the conductor is here now, carry current up. So we see the whole thing from the top view, okay, the top view. So we have this conductor here. A conductor that carry current up will be seen as a point, okay. So the current now is pointing at you. If the current is moving away from you, we are using something like this. Okay, if you have a current that point away from you, okay, this one is point to you, and this one is point away from you. Okay, so this one is away from you, this one is point at you. So it's just like an arrow, right? Just like an arrow. Okay, so if you you watch this how people shoot arrow, when you look at the arrow flying away, you see the feather behind the arrow, right? That is the analogy here. So we have this, and then we need to draw this blue color magnetic field. I don't have a larger circle. I'm supposed to have a larger circle here. Let me find something big enough to draw. Okay. Never mind. I'll use this compass. Okay. Okay, so same size that before. So these are magnetic field. Okay, we don't know in what magnetic field. Okay, and then we assume that we don't walk actually around that. Okay, around that, the exact, what we call it, the exact circle. We assume that we walk around at different paths. Okay, at different paths. All the paths are, let's say, 1 cm. So here, bear with me, there's a lot of drawing to be done here. So we have first one, this is our first movement. Okay, we have this arrow, this is a small displacement, and then followed by this direction, same thing. All the paths are the same, yeah? All the paths are the same, but in different direction. Okay, and then we have this one also, which is quite that one, we call it. Okay, this one is suddenly deep down into, and then after that it go up again. All right, so just follow what I'm doing here. So you see that as long as you cover the whole circle is good enough. Okay, and now we have this. Okay, and then the other one, go back down again into the circle, and then go like this. So I have to draw all these things just to make you more understand. Okay. So now you see that they are all the movement. Let's say this is how you move around lah. You are N, you move around like that. Okay. So now we have this again. And after that, here, you see I use all 1 cm only here. So in your drawing, you might do the same thing also. One more. Okay, don't worry, we are there. We are almost there already. Finishing. This is a part that I had lah. See? Complete. All right, complete. So we assume that we are moving. We have this movement around this. Let's say you start somewhere here. Okay, you start somewhere here. This is your first one. So the lengths here, they are all the same. This is delta L. Every one are the same. Delta L, delta L. So I'm not going to draw every one here. So this one also delta L. Now, you know that is your path, delta L. Okay, your path, this is how you move around, because you don't know how exactly the circle are. Okay, so according to Ampere's, what he discovered is that if we draw the magnetic field, okay, if we draw the magnetic field, blue color here, okay, if we draw the magnetic field, if we multiply this value delta L, okay, delta L, with the component of the magnetic field which is in that direction. See or not? This is a magnetic field. The black color is a magnetic field. So if you take a component, okay, that is in the same direction as this one, okay, same direction as this one. So what's your component? Your component is here. Okay, this is a component of the magnetic field from this part, and another one is a magnetic field from this part here. So altogether, you have this red color magnetic field, total magnetic field. Okay, the total magnetic field, red color. Now, this is actually quite difficult to understand here. This one is for you to know something like this existed. You can imagine people long time ago, this is like few hundred years ago, they can imagine things like this. You are in a modern era, go and search Google for all these more detailed things. So we have this magnetic field. Okay, now this blue one and this blue one combine to become this red magnetic field. Okay, so now we have this magnetic field, which I will also call it by delta B, which is parallel to the blue, to the green displacement, delta L. All right. So what's next is when you multiply, starting from this one. So now you have the first one. So if you call this one is your delta L1 multiplied by this one also 1. Then you have next one, 1, 2, 3, 4. There are so many, right? So what we do is we sum up. Okay, we sum them up. Okay, we have delta L1 dot delta B parallel number 1. You sum up until the last one, delta Ln dot delta B parallel N. What do you get here according to Ampere's law? Okay, so according to Ampere's law, this whole thing here will, okay, is going to be equal to mu naught I. Okay, it's going to equal to mu naught I. Your I is a current I. The mu naught is one of the constant that you call the permeability. All right, or you can say actually the discovery is directly proportional to the size of the current, but because when you put in a constant, it becomes like that. So what we do here is we can actually sum up everything here. Okay, summation of delta L I, and then dot with your delta parallel I also. This total here must equal to mu naught I. Okay, mu naught I, and then our total value I is starting from 1 until n. So that is Ampere's law. Okay, Ampere's law. Of course, mathematically it looks actually difficult, okay, to see. Okay, well, for people that already taught this one for 30 plus years, it's something very easy actually. Okay, so that's why I said always your language of your physics is mathematics. Mathematics is the most powerful language in science, but the difference between mathematics is physics and some physical science. They need to interpret the meaning of the mathematics. Mathematics can be very powerful, but if you are not good at interpreting the meaning of mathematics in physics, you are not going anywhere. Okay, you are not going anywhere. Okay, so that's the difference between the mathematics and what we call that, the science, physical science. All right. So now, if our delta L is very very small, okay, if your delta L is approaching 0, then our equation will be changed, because you become too small, it become D. Okay, it become D. So now it is like this now, D. So this one is normally quite constant throughout the whole circle, right? So we have B, which is parallel dot with this one. Okay, the value already changed. Then your delta L will become DL. So now we dot DL, and because you already changed to differentiation format, so this one will become integration. But you have to integrate everything until you go back to the same point. So that one is called closed integral, and this whole thing is equal to mu naught I. Okay, so again, something new to you. Something new for you today is this closed integral. Okay, closed integral. So this equation is called Ampere's law. So we're going to get 6. Okay, this is called Ampere's law. Okay, Ampere's law. Now, of course, theory is simple. So our application will be, we're going to use this Ampere's law to find out, okay, to find out what is a formula to find out the magnetic field around a conductor. Okay, around a conductor. So that's it. right? So we go to the application, okay? Application, magnetic field due to current. So now we're going to use this one in number E, okay? Number E. So magnetic field due to current. Okay, magnetic field due to currents. Because of current, there is magnetic field existing. So our first one, straight conductor. Okay, our straight conductor. So actually something like this. We want to calculate how strong is a magnetic field when you are at a certain distance from the conductor. Again, we assume that, okay, this is a conductor. Okay, carry current I. Okay, it's carry a current I, and then we have a magnetic field around. We know that we have magnetic field around, so here something like this. Okay, so our magnetic field again the same will be in this direction. Okay, in this direction, and we assume that that distance is R. Okay, the distance here is R. Now, by using Ampere's law, okay, using Ampere's law, we start from here. Okay, so this one dot dl is equal to mu naught I, but we know that the B parallel is always the same. Okay, it's always the same magnitude. So we take out the B, so it becomes this one, dl equal to mu naught I. Okay, and since this one means the total length of the blue area, okay, the total length of the blue circle. What is the total length? That total length is given by this. Okay, given by this 2 pi r, right? The circumference mu naught I. So now we have magnetic field is equal to mu naught I over 2 pi r. So now that is the formula to calculate the magnetic field strength. Okay, magnetic field strength. And normally we drop out that one. Yeah, we normally drop out that one because it's understood that they are all the same everywhere. So this is our equation number 7. Okay, so that is our Ampere's law application number 1. Okay. And the next application will be on solenoid. Okay, solenoid. So we go to page 3 now. Solenoid. Okay, our solenoid application number 2. Solenoid. Okay, that solenoid must be closely wound around. Okay, closely wound around. So something like this. So let's say we have a core, okay, a paper core. Okay, a paper core, and then we have this wire going up and down. Okay, we have wire going up and down like this. The distance between each loop must be very close to each other and very small. So assume that the current is like this. Okay, going up, 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 and down here. So what we want to find is inside the conductor, inside the solenoid. Okay, what is the strength here? Okay, we want to find at this center. So this one is called the center of solenoid, and this one is called the axis of solenoid. Okay, and this one is number of turns and so on. So those are just conductor. Now we're going to cut the solenoid. Okay, so we're going to cut the solenoid so that it's much easier for us to do the analysis. So we only, when we cut like that, you're going to see 1 2 3 4 5 1 2 3 4 5, right? You're going to see 5 conductor up there and 5 conductor down here. Okay, 5 conductor down here. This one current is in, so you draw like this. Current in, current in, current in, and definitely this one out. Okay, this one out. So we have out, 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 out here. All right.